Well, that is a welcome. Thank you very much, Rick. Can you hear me? Okay. So I'm looking forward to spending about 10 weeks in the next 12 months here in College Station and interacting with some of you and maybe with the students on a regular basis. Within the confine of this class, because this is first and foremost a course, I have decided to focus on a topic which is not often addressed in the field of kinesiology, but one that is going to get a lot more recognition over time as the biological basis of the field becomes deeper and more elaborate. And it has to do with some of the less than positive aspect of being exposed to regular exercise. We focus on the good side. We focus on the positive aspects. Like people in nutrition likes to focus on the advantages of combinations of nutrients, etc. Or the physician like to focus on the good side of pharmacotherapy. But there's I wouldn't say a dark side, but there is the other side of the coin too, where you have people who do not respond well, who at times have adverse responses and sometimes deleterious responses. So that's what I will be talking about. We like to focus on this. This is probably the most telling slide in the whole field of exercise and health. And it shows that people who are more fit have a lower rate of cardiovascular disease, a lower rate of cardiovascular disease death, and as well death from all causes as well. I could spend the whole lecture on that slide alone. There's lots of information in that slide. But today I'm going to try to dissect some segment of it and show you in the end that indeed it's real. But there is a fraction of us that does not fit that hyperbole. Okay. And I will focus on some key questions. For example, what is research telling us today about the range of regular exercise-induced responses? And here I'm talking mainly about the biological responses. Are there people who do not improve when exposed to regular exercise? Are there people who can be injured or who can develop adverse responses? And would those people get better if they exercise differently or more strenuously? Those are some of the questions that I think you can relate to, and they will help me anchor the rest of my talk. These questions are very rarely asked in the field of exercise biology, but they are commonly discussed in pharmacotherapy, in nutrition, by nutritionists and physicians alike for caffeine consumption, alcohol consumption, etc. And they are considered as normal expression of normal biological human variation. Let me give you an example. When you consume alcohol, alcohol is metabolized in the liver, and there are several enzymes, but these are the two most important enzymes, ADH, particularly ADH3. So here's what happens when you have a genotype at the ADH3 gene, which translates into an enzyme that's slow. It metabolizes alcohol, but at a slow rate. And other people have an enzyme that metabolizes alcohol at a very high rate. Needless to say, those who have a slow metabolizing enzyme will have a tendency to maintain higher blood levels of alcohol. It takes a longer period of time to get rid of it. Well, we know that there's a relationship between consuming alcohol and HDL cholesterol. There is a pretty strong effect of alcohol consumption, wine and beer and some spirits, on your level of HDL. But look at this slide here. If you don't drink, it does not matter. You all have the same level of HDL. But if you are a drinker and you have the fast metabolizing enzyme, it is as if you were not a consumer of alcohol. You have a low level of HDL. But if the faster your metabolism, the higher the slower your metabolism, the higher the HDL cholesterol. That's an example. It's a very complex pathway, but just one gene has a very strong effect. And the difference here is between 44 and 50 milligram per deciliter. So that's a substantial difference. Another example, even more striking, I think. The response to statin. As you know, statins are prescribed for hypercholesterolemic people. And they have changed the landscape in the management of hyperlipidemia. But some people do not react well to statin. About 2 person per 10,000 persons of years of consumption develop a muscle wasting disease called rhabdomyolysis. But the hypercholesterolemic people who do not take statins, nobody develops that condition. There are about 30,000 people in the US who have this statin-induced myopathy. And it's more frequent when the users are older, when they use high doses of statins, higher frequency in females. If you have chronic kidney disease, you have more at risk, and genetic factors. And let me show you this. There's one gene, this gene, anion transporter in the liver, which is important for the uptake of the drug. If you have that genotype at in the sequence of that gene, if you have the CC genotype, you have about 17 times more risk of developing myopathy if you are taking a statin. 17 times. This explains 60% of the cases of myopathy. That's biological individuality. So statin has tremendous positive effect. It reduces your LDL cholesterol dramatically in most people, but you can have that too. That's an adverse effect. So pharmacotherapy, nutrition, these are fields where people are used to look for and study this. But in exercise, we seem to look only at the positive effects, and we need to become more sophisticated and also include the adverse consequences and learn how to manage them. Develop tools to screen people so that you prevent them completely by screening out those who run the risk of being affected negatively by exercise. So I will talk about these 5 topics. I'll say a word about the variability in response to regular exercise, the normal variance that we see, the risk of injuries to the heart, exaggerated blood pressure response, and then I will look at the topic of adverse response for common risk factors. And then I will finish with some comments on the exercise for all versus exercise for me, the personalized exercise medicine approach. So, human variation in response to regular exercise. When I got involved into this field, the paradigm was this. The more exercise you did, the better the performance, or when we were talking about health, the better the health outcomes. There was a linear relationship. The more you did, the better you were. That was the common thinking. And then I pursued training in genetics, and that changed my mind. There's a famous Texan who wrote a book in 1956 called Biochemical Individuality. He had a profound impact on my thinking in this. He was a professor at UT Austin, retired member of National Academy of Science, a very forward-thinking man before we had the tools to study human variation at the gene level. So I began to do studies to quantify individual differences. And my first paper goes, in this area, goes back to 1984. Many of you were not born. And that paper, it took me a while to find a way to illustrate that properly. It was a few years later that I drew that slide from the data of the 84 paper. And here it is, 47 young men, very, very sedentary. We screened them out among a group of 130. We took the most sedentary, and we exposed them to 20 weeks of exercise. Started 3 times a week, moderate intensity, and build that up such that by about 12 weeks they were training 5 days a week, 50 minutes at 85% of their max. They trained. And look at the gain in VO2 max. The mean gain was half a liter of oxygen, or 20% of their baseline. But the range was from 0 to 1 liter. And they were all young, 18 to 30 years of age. So that was intriguing. We did twin studies, like Dr. Kreider said, and twin studies showed us that monozygotic twins, that members of the same pair, had about the same response, but different pairs were very different. But the most powerful demonstration of the importance of individual differences was in the heritage family study, where we trained families, whole families, parents and offspring, all adults, 17 to 65 years of age, trained them in the laboratories at 4 different centers, and with the same program, very demanding program, and this is what we found. 473 subjects coming from 100 families. And as you can see, the mean gain was about 400 milliliter of oxygen, an increase of about 17%. But the standard deviation was 200 milliliter of oxygen. And as you can see here, there were some people who changed by less than 100 milliliter of oxygen. That's within the error of measurements. In other words, they made no progress at all. But look at the distribution. We have some people who respond very, very well. These people are talented. They are highly trainable. But at the other hand here, and I hope you can you see my mouse on the screen? Good. At the other hand of the screen here, you see these people have almost no gain. 20 weeks of exercise, a lot of investment. It will not be too bad if it was limited to cardiorespiratory fitness, but it is not. It affects metabolism as well. And then when we plotted these gains by families, this is what we found. So here we have the families on the the x-axis, and each bar here, each bar is a family. And within the bar you have dots, and these are the family members. The lowest gainer in that family is here, and the highest gainer in that family is there. And in between we have the others. And as you can see, this is the mean gain. The red line is the mean gain. And as you can see, we have a dot which is the mean of each family. And as you can see, we have here families where just about all the members were below the mean, and here families where all the members are above the mean. The irritability, the evidence for a genetic transmission from parent to offspring was almost 50%. So it's real. It's not just random noise, it's real. There are people who improve more than others. And the challenge, though, is to find the mechanisms. Why is that happening? Okay, so that's human variation. Now let's move now to more extremes. There are people who exercise and will exercise under conditions that are likely to cause damage. Benefits, but benefits cohabitating with damage in other organs and tissues. And that is very important for us. So let's explore that. I will not be able to deal with it in depth, but I will set the stage for you to continue arguing with your professors. Two papers are important. They have addressed that in some depth, and they have done it in a very favorable context. Well done. These are all cardiologists, one published recently the Mayo Clinic Proceedings, and this one this year in the Heart Journal. These are two good papers to use if you want to start looking into this question. So on the basis of these papers, this is what we have. Exercisers, regular exercisers are doing well. On average, they live 7 years longer than non-exercisers. So if you are a non-smoker, you consume a little bit of alcohol, your normal weight, you can cope with the stress, and you exercise, you're adding years. But exercise by itself is about 7 years of difference. But they ask the question, is there a safe upper limit beyond which the adverse effects outweigh the benefits? And the arguments for the presence of this upper dose limit are listed here for the cardiovascular system. Those are seen in the presence of just about only chronic, intense, and sustained exercise. They're not seen at low intensity. They're not seen at moderate intensity. They're not seen with infrequent. They are seen with chronic, intense, and sustained exercise. What it does, in many individuals, it causes myocardial fibrosis, particularly in three areas: the atria, the interventricular septum, and the right ventricle. And what it does, these patches of fibrosis become the site for triggering atrial and ventricular arrhythmias. That's extremely important. It's also associated with coronary artery calcification. We think it's the other way around, but coronary artery calcification studies have shown that there's a higher degree of CAC in athletes who perform intense and sustained exercise. Just the opposite of what is happening if you exercise at lower intensity. It also causes diastolic dysfunction, particularly in the, on the right side of the heart, the right atrium and ventricle. And large artery wall stiffening. Again, this is the opposite of what we generate with moderate intensity exercise. Very, very nice. That's probably a side effects only, but it's very revealing. We have, in people who do these kinds of exercise, an elevation of the clinical biomarkers of myocardial injury, particularly troponin and the beta type of natriuretic peptide, and also the MB form of creatine kinase. And when those are present, for example, after a marathon, an ultramarathon, they are high, and it takes several days for those markers to go down. At the same time, we have a transient, admittedly a transient, reduction in right ventricular ejection fraction. So that's not good. If it happens once, it's not bad. But if it happens repeatedly, you do that often, then it begins scarring, and it leads to this calcification, diastolic dysfunction, and large wall stiffening. For example, the fact that we have these sites of arrhythmogenic veteran endurance athletes, so endurance athletes who are older, have done this for decades, have a 5-fold increase in the prevalence of atrial fibrillation compared to age-match controls who are not exercising at these intensities, and compared to young people who are active. So based on these data, O'Keefe and Chip Levy and their colleagues have looked at the study, a study published in M.Sc last year, where 52,000 adults were followed for up to 3 decades. 14,000 of them were runners and 42,000 non-runners. Overall, the runners, which included, moderate and high intensity, had a 19% lower risk of death over 3 decades. But look at that here. So these are the sedentary controls. If you run from a tenth of a mile to about 20 miles a week, you have about a 25% reduction in risk. But if you run more than 20 miles a week, it disappears. I'm not showing you the confidence interval, but the confidence interval overlap with 1, therefore it's non-significant. There's no difference. You lose the benefit if you do too much. That's what it says. And it says it in the ultimate criterion, death. So it's pretty powerful. Let's look at a couple of studies where this is vividly demonstrated. Here we have lifelong endurance athletes. 12 of them matched with 17 young endurance athletes and 20 match controls, non-active. They use cardiac magnetic resonance plus imaging with a marker called gadolinium. This enhances the visibility of the areas where you have fibrosis. And they found that the prevalence of myocardial fibrosis in the lifelong endurance athlete was 50% compared to 0 in the other 2 groups. And that's pretty strong. Let's look here at arrhythmias. A very large study, 52,000 cross-country skiers. Admittedly, it's not a control study. These are the people who run the 90-kilometer Vasaloppet study in Sweden. That's a very famous cross-country study done in 1 day. On a weekend, 1 day, you start early in the morning and 90 kilometers. Some people do it in a few hours, the athletes. Others do it almost in 3/4 of a day. And they monitored 52,000 participants from 1989 who did the run in 89 to 98, and then they followed them until 2005. Almost 1,000 of them experienced arrhythmia during the follow-up. And those who were the top athletes, the best finishing time, had higher risk of arrhythmias. There was a 5-fold difference. So that is not good. That's not something that you want. It puts you at risk for sudden death, for example. O'Keefe and Chip Levy have developed this model which says that extreme exercise efforts have a number of cardiovascular and physiological and biochemical alterations that immediately have effects on the heart. Right heart strain, diastolic dysfunction, etc. When you continue repeated that, you induce subacute effects such as cardiac fibrosis. Long term, you have increases in the chamber size, patchy area fibrosis, arrhythmias, both in the atrial and the ventricular areas, and a greater incidence of sudden cardiac death. And chronically repeated, it leads to dilatation of the left ventricle, hypertrophy of the tissue, increased left ventricular mass, and that cycles continue to repeat itself and creates a biological environment for a catastrophe to occur, even though you're doing this to be healthier. So that's one aspect. Another one is in the exaggerated blood pressure response. That's also not that rare. There are people who exercise and acutely they show an exaggerated blood pressure response. So let me show you a couple of studies that have looked into this. Here, this is a paper published recently in which they took a cohort of 10,000 normotensive individuals. who had performed an exercise treadmill test. So a pretty substantial group. And they defined the exaggerated blood pressure response as having an increase in systolic blood pressure of greater than 7.5 millimeter mercury per met, or a systolic blood pressure at peak exercise higher than 220, or a change in diastolic blood pressure of more than 15 millimeter of mercury compared to resting diastolic. A prevalence of about 13% of their cohort met that one of these three definitions. So again, not a small number. And another study looked at the prevalence of these exaggerated blood pressure response in people who were otherwise healthy and others who had the metabolic syndrome, to see if it was occurring more frequently. Well, it's a small study for these kinds of investigations. 95 subjects with metabolic syndrome, 230 without. The prevalence of exaggerated blood pressure was 31% in those with the metabolic syndrome versus 14% in those without. Notice that 14% is pretty close to the 13% from the first study. So that's concordant, but it's more than it's a twofold difference, and they have a 2.3-fold higher risk if you have the metabolic syndrome. So that is something that we don't worry about, but a lot of people, if you don't monitor it, you don't know, and it happens while people exercise. Okay, now I'm going to talk about some of the research we have done. Common risk factors. When we exercise, we tell people, if you do it, you're going to have a better blood pressure. You're going to become more sensitive to the action of insulin. Therefore, that offers protection against glucose intolerance. You're going to have higher HDL cholesterol and lower triglycerides. A cardioprotective profile will result from you being physically active. And that's true for the vast majority of people. But let me show you some data that challenge this view. So here, this is based on the Heritage study. We had a cohort of about 500 whites and about 250 African American in that study. Same exercise program, 4 clinical centers. And each trait we measured, I forgot to tell you that about, I showed you the changes in maximal oxygen uptake before. Forgot to tell you, everything in Heritage we measured twice before and twice after. And if there were big discrepancies between the two, we had to reject some subjects for these particular analysis. So here, this is based on 2 measures of fasting insulin before the program, 2 measures after the program, one 24 hours after the last exercise, the other 72 hours after the last exercise. So a lot of people, therefore, here, about 700 subjects in that slide. We think that with exercise, and that's what we teach, you will have a reduction in fasting insulin. That's the dogma. Well, all those in green here seem to have a reduction in fasting insulin. Those here in the blue, they are within the error of measurement, I would say. They're close to the baseline. They move in the right direction, but not deep enough to say they really have improved. Likewise, those in the purple here, they may have had an increase, but it tends to, we have to interpret that as something within the measurement error or day-to-day variability in the measurement. But the red ones, there's cause for concern. Even though the mean decrease was 7 picomole of insulin, the standard deviation was 32, so huge standard deviation. So here, when I saw these data many years ago, I began to think about a way to analyze that, to have objective criteria to decide what is a positive response, what is a non-response, and what is an adverse response. And it took a while before we were able to achieve that. And we summarized all of our findings in that paper published a year ago. And here is what we found. How should we define an adverse response? So we were very lucky in the Heritage Family Study. We had 60 subjects that were at the same inclusion and exclusion criteria as the regular subjects of Heritage. But we measured them 3 times over 3 weeks. So we used that to calculate what is the normal day-to-day variation in the particular trait of interest. And since we do the assay at the same time, we have a combination of the day-to-day variation plus the measurement assay variance. So to make this clear, let's take, for example, here, systolic blood pressure. So here, the 60 subjects were measured 3 times. The average measurement was about 119 over, I don't know. But the standard deviation of that was 10 millimeter mercury. We had a technical error of 4.9, a coefficient variation of 4, and the intra-class correlation of 0.76. So we decided to use that and use the technical error here, which recapitulates the day-to-day variation plus the measurement error of the blood pressure itself. And we did it for fasting insulin, HDL cholesterol, triglyceride, and resting blood pressure. And here is our reasoning. So to make sure that we're not dealing with people in the middle, but we're really capturing those who are moving in the adverse direction, in the non-desirable direction, we're going to take 2 technical errors, 2 standard deviation of the day-to-day variation. For example, for blood pressure, it'll be 2 times 5 millimeter of mercury. So anybody who, instead of decreasing blood pressure, increases systolic blood pressure by 10 millimeter of mercury and more is an adverse responder. And how prevalent is that then? Well, here we have for blood pressure, the red is the part of the distribution where the response is adverse. And so for blood pressure, you see the proportion who have adverse responses for triglycerides, for fasting insulin, and for HDL cholesterol. That's in Heritage. Then we decided that, yeah, that's good, but we need to replicate that. We cannot rely only on one study. So I talked to colleagues, and we had a number of cohorts that we added. We added a cohort of Drew, Tim Church, Inflame also from Tim Church, Stride from Bill Krause at Duke, University of Maryland with Jim Agberg, and a group in Jyväskylä in Finland, about 1,700 subjects. So for fasting insulin, 8% of the subjects had that adverse response profile. For HDL cholesterol, 13%. For triglyceride, 10%. For systolic blood pressure, 12%. So overall, for any factor, each individually, taken individually, there were about 10% of the people who were not doing better. They were doing worse. Now, they may have been doing better for the others, but it matters. For example, if you are pre-diabetic and you exercise to improve your risk of not becoming diabetic, and you experience an increase in fasting insulin, which suggests a decrease in insulin sensitivity, you're setting yourself up for trouble. The same for example, HDL cholesterol or systolic blood pressure in, say, people who have had an infarct and who are in cardiac rehabilitation. Now, here is the proportion of, in each of the study, of people who had at least one adverse response, 30%. 30% out of 1,700 had at least one adverse response. 6% had 2, and another 1% had 3 or 4. So there are about 7% of the population when they exercise, moderate intensity, 7% who have at least 2 factors moving in the wrong direction. And we don't know it. Now, there may be, if we were measuring the whole cardiometabolic profile, there may be 50 variables that are of interest, and they may be moving in the right directions for 40 of them. But there are some that are affected negatively, and we need to learn how to deal with this. Now, next question. Can we identify them a priori? That would be ideal, because then we can screen and personalize the exercise. Among these 1,700 subjects, I can tell you this. They are equally present in men and women, same prevalence in young and older adults. There was no difference between white and African Americans. It was not associated with baseline VO2 max at all, not associated with the gains in VO2 max. It was observed at about the same rate in all the programs, and they were different programs. And it was observed in people on medication and those who were not on medication. So in other words, we couldn't find a single predictor among the things that were available in all the cohorts. Not a single one. So that brings me to this. Ideally, and this is something that the field must embrace as soon as possible, we need to move to personalized medicine, personalized exercise prescription. Yes, the we exercise is important for public health, absolutely. But I think these observations will force us to perhaps put some boundaries around the messages in the public health arena, because if we recommend things that are maybe pushing the limit a little bit, the risk of adverse responses increases probably exponentially. So public health has to stay within the safest possible territory. And when we want to go beyond that, I think it'll have to be personalized. But that requires that we develop tools to be able to achieve this. So let me elaborate on this in the next, I don't know how much time, about 7-8 minutes. Mike is telling me 15 in the back.
No, I'm telling you 5.
Well, you said that 3 times. Human variation in response to exercise is considerable. There's a strong genetic component. We have poor responders, we have non-responders, and we have adverse responders. And by the way, I didn't deal with that, but it also is found for exercise and joint, muscle, and tendon biology. Sudden cardiac death is rare, fortunately. I didn't have time to deal with this, but that's also one of the adverse consequences, the ultimate adverse consequence of exercise for some people. About 30% of a participant experience at one adverse common risk factor response, and about 7 to 10% will experience multiple. And then, based on the observation we had across these 6 studies, it's very unlikely that we will transform an adverse response profile into a more favorable response profile with more pain, with more intense exercise. I dealt with this, so I'm going to skip that. That's a summary of why some of this occurs. Because I want to go to the last 3 or 4 slides to tell you that there is hope. You remember that the Health and Human Services Physical Activity Guidelines, American Heart Association, and ACSM guidelines are calling for this: 150 minutes of moderate intensity physical activity. That is the public health message, and that message seems to be pretty safe for most people. There will be some that will experience adverse responses, but it will be a really small minority. There will be more adverse responses if we go to 75 minutes per week of vigorous exercise. There we'll have more adverse responses. It's still probably reasonable for a public health message, but we can expect more adverse responses. So because the second part is closer to the upper dose where we begin to have the balance between adverse and benefits. So let me suggest you a way out of this. And one way out of this is to find genomic predictors. Because if we could, these genomic predictors could be identified at any time in your life. In a couple of decades, this would be done at birth for all of us, well, for all of you. And then the risk profile that you have will be known to you. But we need the data. So what we have done here, we have in this paper, we have, I think, provided a path to show that it can be done. And the phenotype that we have used here, I could have used other papers, but this one provides a nice illustration. When we exercise at a progressively increasing intensity on the test, before and after a program, after the program we know that the heart rate goes down for the same workload. We expect that, a decrease in heart rate. So in heritage, I took 50 watts because at 50 watts, this is our white sample, everybody could accomplish that on the bike. And the mean decrease in heart rate before and after training, 2 tests before, 2 tests after, was 11 beats per minute with a standard deviation of 10, and the irritability, the family lines showed that the irritability was 34%. So all these people experience a decrease. But look here, there are people after 20 weeks of exercise who had a higher heart rate at 50 watts. And not a small number, about 150 almost. No, 100. So we did a genome screen, 320,000 genomic markers covering all the chromosomes, and we identify 9 DNA variants that predicted the whole irritability. These 9 variants provide all the information that we capture in the 34% irritability. And the variants are in these genes here. We repeated the analysis by controlling for each of them, and as you can see, the irritability goes down, 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 and we account for all of it with these 9 markers. Perfect, bingo. The problem is that we don't have any cohort where we can replicate this. That'll be fun. But let me show you what it does. So we have 9 variants. At each site, you have inherited 1 allele from your father and 1 from your mother. So you have 2 alleles. So we are asking at each site, how many alleles, how many versions of the genes do you have that are associated with the lowering of the heart rate? We count them. These are the good alleles. The more you have here, if you have 16 or more of the possible maximum of 18, 9 times 2, if you have 16, your decrease was not 11 beats per minute, but it was more than 20. But if you have 9 or less, it was 0 change. So that is a predictor of your ability to benefit from the perspective of hemodynamic changes when you exercise. Then, I'm showing you now the coded version, the color-coded version of it. The green are the ones who improved a lot, and the red, less. So now we went back to the whole cohort, and we look where the subjects are falling. Well, as you can see, we predicted a lot of the bad responders. A few of them are close. One of them should have been picked, but was not by our genomic predictors. But we pick also all the very good predictors. Look, they're all concentrated here. So the predictors seem to be working. Not perfectly, but certainly as well as BMI works to predict obesity, for example. So I think if we had more of this, we would have the tools to move in a very favorable direction. If we could have this for the response of insulin to exercise, the response of HDL cholesterol, of blood pressure, etc., and have a composite genomic predictors of your ability to benefit from exercise, or rather we may want to phrase it the other way around, the inability to benefit or develop adverse responses, then we could advise individuals. That's personalized exercise medicine. And that's obviously the way of the future. So the model is this, a general model. When you exercise, you improve fitness, you improve health and performance if you are interested in performance. And at each of these arrows, red arrows, indicates a site where the genes can intervene. And the genes and the cellular environment and your biological individuality, not only in the genes, but also in the proteins, in the catabolic products of metabolism. So the molecular signature that we need to do a good job for personalized medicine requires all of these omics and including the genomics, and we need an integrated view of that. It's going to take decades of research, but exercise biology has to move in that direction. I would close on that. Thank you very much.